According to the National Electrical Code, specifically Section 310.4, conductors in multiple raceways are permitted to have different sizes. However, there is a crucial stipulation: the ampacity of each conductor must not exceed the ampacity of the corresponding service entrance conductor. Let's break down what this means in practical terms. Imagine 2 meter banks, each with its own service conductor and conduit. One meter bank feeds 4 meters and has 2 number 2/0 wires and 1 number 1 wire. The other meter bank powers 5 meters and utilizes 2 3/0 wires and 1 2/0 wire. The question arises: do all 6 wires need to be the same size even though they're in separate raceways? The answer, based on the NEC, is no, but with conditions. The first condition is the ampacity of each conductor must be considered. Let's examine the ampacities of the mentioned wire sizes. A number 2/0 copper conductor typically has an ampacity of 200 amps. A number 1 copper conductor has an ampacity of 175 amps. A 3/0 copper conductor has an ampacity of 300 amps. Given these values, as long as the ampacity of each conductor in each raceway doesn't exceed the corresponding service entrance conductor's capacity, different sizes are acceptable. Consider the meter bank with 4 meters and its conductors, 2 number 2/0 wires at 200 amps each and 1 number 1 wire at 175 amps. Now look at the meter bank with 5 meters featuring 2 3/0 wires at 300 amps each and 1 2/0 wire at 200 amps. Since the ampacities are within permissible limits for their respective service entrances, using different sizes is allowed. There are other things to keep in mind. Firstly, raceways must be installed according to the NEC requirements for conduit fill, specifically outlined in Section 310.16. Conduit fill refers to the maximum percentage of the conduit's cross-sectional area that can be occupied by conductors. Exceeding this limit can lead to overheating and potentially damage the wires. Secondly, conductors must be properly sized for the load they will carry. This ensures that the wires can safely handle the current demands without overheating or causing voltage drops. Use calculations specified in Article 220 of the NEC to determine the minimum conductor size required for the anticipated load. Thirdly, service entrance conductors must be terminated in an approved manner as per Section 250.118 of the NEC. This involves using appropriate connectors and ensuring proper grounding to prevent electrical hazard. The NEC specifies acceptable methods for grounding and bonding service entrance conductors to ensure safety and minimize the risk of electrical shock. To summarize, while the NEC permits the use of different sized conductors in separate raceways for service entrances, it's crucial to adhere to the ampacity requirements outlined in Section 310.4. Additionally, proper raceway installation, conductor sizing for the load, and approved termination methods are essential for safe and compliant electrical installation. Let's further expand on the considerations for service entrance conductor sizing and installation. We'll delve into ampacity adjustments, voltage drop calculations, and the importance of proper labeling. Ampacity adjustments are necessary when conductors are installed in environments with higher ambient temperatures or when multiple conductors are bundled together. The NEC provides tables that specify dirting factors to apply to the conductor's ampacity under these conditions. For example, if conductors are installed in a hot environment, their ampacity must be reduced to prevent overheating. Similarly, if multiple conductors are bundled together in a raceway, their ampacity must be derated to account for the increased heat generated. Voltage drop is another critical factor to consider when sizing service entrance conductors. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it's often necessary to increase the size of the conductors. The longer the conductor run, the greater the voltage drop, and the larger the conductor size required. Proper labeling of service entrance conductors is essential for safety and maintenance purposes. The NEC requires that all conductors be clearly identified with their size, voltage rating, and function. This helps electricians and other qualified personnel to easily identify the conductors and avoid accidental contact with energized parts. Labels should be durable and resistant to environmental factors such as moisture and sunlight. In addition to these considerations, it's also important to comply with all applicable local codes and regulations. Local codes may have additional requirements or restrictions that are not covered by the NEC. It's always best to consult with a qualified electrical inspector to ensure that your installation meets all applicable requirements. To reiterate, the NEC allows for different size conductors and separate raceways for service entrances, provided that the ampacity requirements are met and other factors such as conduit fill, conductor sizing for the load, and termination methods are properly addressed. Ampacity adjustments, voltage drop calculations, and proper labeling are also important considerations. By following these guidelines and complying with all applicable codes and regulations, you can ensure a safe and reliable electrical installation. Let's explore specific scenarios and examples to further clarify the application of NEC 310.4. Scenario 1: a residential service entrance consists of two separate conduits, each containing 3 conductors. One conduit feeds a main panel, and the other feeds a subpanel. The load calculation for the main panel requires 2 number 2/0 copper conductors and 1 number 4 copper conductor for the neutral. The load calculation for the subpanel requires 2 number 1/0 copper conductors and 1 number 6 copper conductor for the neutral. In this scenario, the conductors in the 2 conduits are permitted to be of different sizes, as long as the ampacity of each conductor is sufficient for the load it serves and does not exceed the ampacity of the corresponding service entrance conductor. The number 2/0 copper conductors have an ampacity of 200 amps, the number 1/0 copper conductors have an ampacity of 150 amps, the number 4 copper conductor has an ampacity of 85 amps, and the number 6 copper conductor has an ampacity of 55 amps. As long as the loads on the main panel and subpanel do not exceed these ampacities, the installation is compliant with NEC 310.4. Scenario 2: a commercial building has 2 separate service entrances, each fed from a different transformer. One service entrance supplies power to the lighting and receptacle loads, while the other supplies power to the HVAC equipment. The load calculation for the lighting and receptacle loads requires 3 500 kcmil copper conductors per phase. The load calculation for the HVAC equipment requires 3 350 kcmil copper conductors per phase. Again, in this scenario, the conductors in the 2 service entrances are permitted to be of different sizes, as long as the ampacity of each conductor is sufficient for the load it serves and does not exceed the ampacity of the corresponding service entrance conductor. A 500 kcmil copper conductor has an ampacity of approximately 380 amps, while a 350 kcmil copper conductor has an ampacity of approximately 310 amps. As long as the loads on the lighting and receptacle circuits and the HVAC equipment do not exceed these ampacities, the installation is compliant with NEC 310.4. It's important to note that these are just examples, and the specific conductor sizes required for any given installation will depend on the load calculations and other factors. Always consult with a qualified electrical engineer or electrician to determine the appropriate conductor sizes for your specific application. Let's discuss the implications of using aluminum conductors versus copper conductors in service entrances. Aluminum conductors are often used as an alternative to copper conductors due to their lower cost. However, aluminum conductors have a lower ampacity than copper conductors of the same size. Therefore, when using aluminum conductors, it's necessary to increase the conductor size to achieve the same ampacity as a copper conductor. For example, a number 2/0 aluminum conductor has an ampacity of approximately 175 amps, while a number 2/0 copper conductor has an ampacity of 200 amps. To achieve an ampacity of 200 amps with an aluminum conductor, it would be necessary to use a number 3/0 aluminum conductor, which has an ampacity of approximately 225 amps. When using aluminum conductors, it's also important to use connectors that are specifically rated for use with aluminum. Aluminum conductors are more prone to corrosion than copper conductors, and using the wrong type of connector can lead to loose connection and overheating. In addition to conductor size and connector type, it's also important to consider the expansion and contraction properties of aluminum conductors. Aluminum conductors expand and contract more than copper conductors with changes in temperature. This can put stress on the connections and lead to failures. To mitigate this risk, it's important to use expansion fittings or other methods to accommodate the movement of the conductors. In summary, when using aluminum conductors in service entrances, it's crucial to carefully consider the ampacity, connector type, and expansion and contraction properties of the conductors. Always consult with a qualified electrical engineer or electrician to ensure that the installation is safe and compliant with all applicable codes and regulations. Now, let's shift our focus to the grounding and bonding requirements for service entrance conductors. Grounding and bonding are essential for protecting people and equipment from electrical shock hazards. The NEC specifies detailed requirements for grounding and bonding service entrance conductors to ensure that the electrical system is properly grounded and that any fault current will flow safely back to the source. The grounding electrode system is a critical component of the grounding system. The grounding electrode system consists of one or more grounding electrodes that are connected to the earth. Common types of grounding electrodes include ground rods, ground plates, and metal underground water pipes. The NEC specifies the minimum size and type of grounding electrode required for different types of electrical systems. The grounding electrode conductor connects the grounding electrode system to the service equipment. The grounding electrode conductor must be sized according to the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding electrode conductor for different sizes of service entrance conductors. Bonding is the process of connecting all metal parts of the electrical system together to create a low impedance path for fault current. This includes bonding the service equipment, metal conduits, metal enclosures, and other metal parts of the electrical system. The bonding jumpers must be sized according to the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the bonding jumpers for different sizes of service entrance conductors. In addition to these requirements, it's also important to ensure that the grounding and bonding connections are properly made and that they are protected from corrosion. Use appropriate connectors and ensure that all connections are clean and tight. Also, protect the connections from moisture and other environmental factors that can cause corrosion. In conclusion, grounding and bonding are essential for protecting people and equipment from electrical shock hazards. The NEC specifies detailed requirements for grounding and bonding service entrance conductors. By following these requirements and using appropriate materials and installation methods, you can ensure that the electrical system is properly grounded and that any fault current will flow safely back to the source.